Hi everyone, Mr. Lee here. In this video, we are going to go over integrals, also known as the antiderivative. All right, let's begin. So in order to understand integrals, we need to understand derivatives. So let's do a quick little review. If I am given a function, let's say a position time function, so x of t is equal to 3t squared. This is my position function. So if I were to graph it, we would get something that looks like this. xt and a graph that looks something like this, right? So if we were to take the derivative, and I'm going to do this step by step, so we would get dx, okay, because we're taking the derivative of x right there, and I'm going to do the power rule, right? So here originally we have a 3, so that's my constant. I'm going to pull it out to the front, but then I have this 2 exponent, and I'm going to bring the 2 exponent to the front as well. So we get a 3 times 2. And then we have the original variable here, t, and then it's 2 minus 1. And this entire thing is being multiplied by the changing of the variable, which is dt, all right? So what this shows us is as we take a tiny bit of time, right, as we change the time by a tiny little bit, we can expect the position to change by a tiny little bit, right? That's what dt and that's what dx is telling us. So if I were to clean up this step, I would get dx is equal to 3 times 2, which is 6, t, 2 minus 1, so that is just t to the 1 power dt. I'm going to clean this up even a little bit more. dx is 6t, t to the 1 is just t, dt, and finally I'm going to make sure all of the tiny little changes are together. So I'm going to say dx divided by dt is equal to 6t, right? And I did that in this step here by dividing both sides by dt. All right, so this is how you go through the whole derivative process. Now, what this function here, dx dt, is equal to 6t, what that function tells us is how much this slope is, or this function is changing by, right? It tells us the slope. And that's important to know. I'm going to put that as a little star there. Derivative gives us slope, okay? And a way that I like to think about it is this dx dt, that's always going to be in a change in y over the change in x notation. And y, of course, being the y-axis and x being the x-axis, right? I know x over here is in the y-axis, but that's just position. And this can be thought of as your rise over your run, okay, which is your slope. So the derivative gives us the slope at a certain point for that function. So as a review, right, if I were to take a look at that point right there and be like, what is the slope at that point? We can say, we can take a look at this dx dt, and let's actually go through it. Let's say this time right here, let's say this is time of 3 seconds at that point. We can say that at that point, according to my derivative function, right, I'm going to do this all in red, dx dt, right? So we can do 6 times 3 because it's at 3 seconds. We can say that the slope at that point is going to be 18, and this will be meters per second, right? So at that point, our slope is going to be a value of 18, and we can plot it, right? And in fact, if we plot it, we get something that looks like this. We get a straight line. Okay, so we can see that as our time is changing, so is our position, and we get this this graph right there. All right, so let's go on into the integral. So that was just a quick little recap on derivatives. So the integrals is going to go in the complete opposite direction. We're trying to reverse things. So I'm going to actually erase this all right here. Okay, if you have yours, that's fine. I just want to make sure that we see everything together. All right, so in order to take the integral, you're going to be given a function. So we're going to start off with the function that we found, which is going to be dx dt is equal to 6t. All right, so we're starting off with that. And if the problem says find the integral for this function. Now, what we're about to find is this thing called a indefinite integral. Okay, and I'll explain to you what that means in a little bit when we go into definite integrals. All right, so in order to find the integral of 6t, we have to take our steps in reverse. So we're starting off here. Let's do this in a different color. So the next step that we had to do is we have to separate the dx and the dt's, and that's very important. Okay, so you got to think about it like this. I want to multiply both sides by dt, right? Because I want to make sure the variables t and dt are together, right? So that's important in the fundamental understanding of what a integral gives us, right? This integral is telling us that we are changing the time by a tiny little bit of amount, and therefore we need to have the time together, time variable. So this dt tells us that we're changing time by a tiny little amount, and therefore when we take the integral, we need to have the variable that it is associated with together. Okay, so this has to be together. So that's the next step. All right, so let's go into the following steps there. Now, the symbol for a integral is a squiggly line, right? It kind of looks like a S, but you kind of like stretch out the S a little bit. So I'm going to show you what the next step would look like. I'm going to put that squiggly long S next to dx. Okay, I'm going to put it also here in front of 6t dt. Okay, now this is a very important step. Okay, so when we go from here to here, and the next step is very important. What you have to do is you have to identify what are my constants, okay, on both sides of the equal sign. So if I take a look here, dx, that is not a constant. That's my changing variable. Okay, so I can't take out anything there, so I'm just going to leave it as dx. But on my right-hand side, I see that the variable that I am integrating is t, right? And I know that because it's dt, right? I'm supposed to be looking at all of the t variables. Therefore, that 6 that is associated with the 6t, the 6 is a constant. I don't care about that 6. I only care about the t's. So what I'm going to do is I'm going to pull the 6 out to the front. So what we're left with is t dt. Okay? All right. What I'm going to do next is we're going to go in the reverse derivative order. So this dx, if I were to integrate this dx, well, technically, I'm going to write in front of this dx, there's like a number 1 there. So you got to remember, if there's a 1 technically in front of this dx, what gives us just 1 when we integrate? So over on the side, what gives us a 1 when we take a derivative? I'm going to do a little example over here. Let's say we have a function y is equal to x, right? So if we take the derivative of this function, we will get dy is equal to, the derivative of just x would be just 1 and then dx. But in math, if we have a 1, oftentimes we just ignore that 1 and we just get dx. So that's what this dx is telling us here. If we just have that dx, the reverse of that is just the original variable. And so what we would get here, the antiderivative of this dx would simply be x. Okay, and that follows this line of derivative. All right, now let's try the right-hand side. So on the right-hand side, we have the 6, and we're just going to bring that 6 out to the front because that's a constant, and we're not trying to integrate that 6. We're only trying to integrate anything that has the variable t in it. Now, before we go into the rules of integration there, let's go over quickly the rules of derivatives. So if you remember from the power rule, step 1, right, we would multiply by exponent. Okay, we will bring the exponent out to the front as we see over here. Right, we will multiply the front by the exponent, and then step 2, we would subtract exponent by 1. Okay, and as we see that right there, we'll subtract the exponent by 1. So the rules for integration would be the reverse. Okay, instead of multiplying by the exponent, we would actually have to divide by the exponent. Before we do that, we have to take a look at the reverse of the subtracting the exponent by 1. We would have to add the exponent by 1. All right, so let's try that over here. All right, so let's use these rules. Now, right now, here we have t to the 1 power. So what I'm going to do is I'm going to actually write that down here, we have t to the 1, right? So the first step is to add 1 to this 1, right? And what we get is the number 2. And then we're going to divide this t by 2. So there's going to be something like this. Okay, so that's what the integral of just t dt will become. And so if I were to clean this up over here, what we would get is, so I'm going to put that in parentheses, we would get 1/2 t squared, okay, and just put the end parentheses there, right? Okay, and so we've successfully taken the integral of t dt, and the integral of t dt gives us 1/2 t squared. And if we were to just clean this up, we will get 6 times 1/2, which just gives us 3, and then this is just t squared, like so. So we will get 3t squared. All right, now let's compare our answers. So the original function that we started off with was x is equal to 3t squared, and our ending function is 3t squared. So we have successfully reversed the derivative, which is what the integral tells us, right? All right, so in the next video, I'm going to go over more examples, but before we do that, I want to make sure you understand what integrals actually tell us, right? What this whole process is giving us. So if we're given a quick little graph, right? So let's say this is the y and this is the x, okay? And we're given, let's say, a curving line like this. If we were to take the derivative of this, we would be finding the slope at certain points. Now, what the integral tells us is the area under the curve, okay? And I like to write that as the AUC. Now, we got to think about it, right? Slope, which is derivative, okay? And slope is everything about division, okay? And if integrals are the antiderivative and the opposite of division is multiplication, multiply, right? This gives us the area under the curve. We're doing basically base times height, right? Which is the basic formula for area. So we're multiplying for area under the curve, and that's what gives us the integral. So if the derivative tells us the slope at specific points, what the integral tells us is how much area is underneath of this line. And so it would tell us, like here, how much area exists. Now, because it's an indefinite integral, this would go on for however long the function is. But what I just showed you right there, from this point to this point, what that's called is a definite integral. And in the next video, I'm going to go over a couple of examples on how you can solve for that. All right. Now, there is another video that you will watch that goes into exactly what the integral tells us. Now, this right here was just a very roundabout way of looking at integrals, because the actual calculus and the actual theory behind integrals is really quite interesting, right? So you're technically taking the area under the curve, but in order to get to that point, the mathematicians over the years, we were able to look at this problem in a different way to get to where we are today. All right, so I'll see you next time. In the next video, we're going to go over a couple of example problems, as well as the definitive integral problems. I'll see you then.